All right, today we are going deep. No, I mean really deep. We're talking about the hidden engine that powers our entire planet. It's this incredible force that's working on a scale that is just, well, it's almost impossible to wrap your head around.
So, have you ever wondered what's the invisible force that's actually moving entire continents, or building massive mountain ranges, or fueling volcanoes? We see all these things on the surface, but they're not random. They're all connected, all driven by one single, absolutely gigantic process happening way, way below us.
And the answer? It's literally right under our feet. We're talking about the Earth's mantle. Now, this is a massive layer of what is, for all intents and purposes, solid rock. But, and this is the crazy part, over millions and millions of years, it behaves like a super thick, slow-moving liquid. It's this gigantic, slow-motion river of rock that's just been constantly churning. So, yeah, let's get into it.
To really get a grip on this, let's start with a simple picture. Imagine our entire planet is just a giant pot of really, really thick soup that's been simmering for eons. Okay, so the official term for this is mantle convection, and it works pretty much exactly like that pot of soup, right? The hotter stuff at the bottom, which is less dense, it rises up. When it gets to the top, it cools down, gets denser, and then, it sinks right back down again. It's this constant slow-motion loop, and it's all driven by the simple physics of moving heat around. So, you might be asking, what's keeping the stove on under this planetary pot of soup? Well, the heat comes from three main places. First up, you've got the slow decay of radioactive elements. Think uranium, thorium, stuff like that, just scattered all through the mantle. Second, there's the leftover heat from when the Earth was first formed, this incredible heat from billions of years ago that's still radiating out. And third, you've got heat literally leaking out from the super hot core. You put all that together, and you've basically got a colossal heat engine running our planet.
Now, how do we know the mantle is actually churning? Well, scientists have this thing called the Rayleigh number. Basically, it's a measure of whether a fluid's going to convect or just sit there. For convection to start, you need a number over, say, a couple thousand. The Earth's mantle, its number is over 10 million. So the big takeaway here is that our planet's engine isn't just barely turning over. Oh no, it is running in absolute overdrive. So we've got this massive churning system. But remember that part about cooling off at the top? What does that actually look like on a planetary scale? Well, this is where the whole story of plate tectonics really kicks off.
See, the very top layer of the Earth, the crust and the upper bit of the mantle, forms this cold, hard, rigid shell. We call it the lithosphere. And if we go back to our soup analogy, this is exactly like that cool, thick skin that forms on top of the pot. And that skin, well, it's not one solid piece. It's broken up into all the tectonic plates we learn about in school. But here's the thing. That skin doesn't just float there forever. As it cools, it gets heavier, denser than the hot, gooey mantle underneath it, and eventually it cracks and it starts to sink. This whole process is called subduction, and you have to understand this is the main event. It's the most powerful part of the whole engine. That immense gravitational pull of these huge, cold, sinking slabs of rock is what's really pulling the rest of the plates across the planet's surface.
And this leads us to one of the biggest mysteries in all of geophysics. Okay, so these massive slabs of the Earth's crust are plunging back down into the mantle, but where do they end up? Do they just sink all the way down to the core, or do they hit some kind of roadblock along the way? Turns out the answer is, well, it's pretty complicated.
All right, so we've covered the sinking part of the cycle. But in a loop, what goes down must come up, right? So where's all that hot rock rising back to the surface?
Well, it turns out it happens in two main ways. First, you've got what's called passive upwelling. This happens at mid-ocean ridges. Think of it this way. As plates are getting pulled apart, it creates a gap. Hot mantle material just sort of rises up to fill that space. It's not pushing its way up, it's just filling a void. But then you have active upwelling. These are mantle plumes. These are like giant blowtorches of super hot rock rising from deep, deep inside the mantle. They're so buoyant they punch right through the crust and they create volcanic hotspots. Hawaii is the classic example.
Now, even though the mid-ocean ridges are doing most of the work creating new crust, these mantle plumes are a huge deal. It's estimated they're responsible for about 10% of the total heat escaping from the Earth's interior. For features that are relatively small, that is a massive amount of energy.
Okay, let's circle back to those sinking slabs of crust, because this is where we get into one of the biggest, most heated debates in geology. I'm talking about the mystery of the 660-kilometer boundary.
So, way down in the mantle, at a depth of about 660 kilometers, something weird happens. We know this because seismic waves from earthquakes suddenly change speed right at that level. What's going on? Well, the pressure is so intense that the very crystal structure of the minerals changes. And this transition zone seems to act like a kind of barrier, which really messes with our simple picture of one big convection loop.
And for decades, scientists have been arguing about what this barrier actually means for the whole system. As one paper I read put it, the prevailing opinion is oscillated between these two rather extreme hypotheses. Basically, the community has been swinging back and forth on this for a long time.
So, what's the big debate? It's basically one system or two. On one side, you have the layered convection idea. This suggests the upper and lower mantle are mostly separate, and those sinking slabs hit the 660-kilometer boundary and just stop, spreading out like pancake batter. And this idea is supported by some chemical data. But then you have whole mantle convection. This side says no. At least some of those slabs are massive enough to punch right through that boundary and sink all the way down. And we have seismic images that look a lot like that. The real answer? It's probably somewhere in the middle, a messy hybrid of both. Okay, so this whole complex system, with the moving plates, the sinking slabs, the rising plumes, it might feel like this is just how rocky planets work, right? But it's not inevitable at all. And to see just how special our situation is, all we have to do is look next door to Venus. Think about it. Earth and Venus are practically twins in size, but geologically they're worlds apart. Earth has what we call mobile lid tectonics. Our lid, our crust, is broken and it moves around. This lets heat escape steadily, like a simmering pot with the lid slightly ajar. Venus, on the other hand, seems to have a stagnant lid. Its crust is one solid piece, so the heat just builds and builds and builds until, maybe, it erupts in these catastrophic planet-wide resurfacing events. In fact, it looks like the entire surface of Venus was repaved in lava about 500 million years ago.
And this right here is the key takeaway. Mantle convection almost certainly happens on other rocky planets, but the way it happens on Earth, our specific brand of plate tectonics, is not guaranteed. It's a special case. And it's this unique style of letting off steam that recycles our crust, helps regulate our climate, and is ultimately a huge reason why Earth is this dynamic, living world and not Venus.
So when you think about it, this churning, slow-motion river of solid rock deep beneath our feet is so much more than just geology. It's the engine that literally built the world we know. It shaped our continents, it formed our oceans, it influences our climate. And even with everything we figured out, it's still holding on to so many secrets, not just about our planet's past, but about its future too.